What is going on, guys? Welcome back. In this video today, we're going to build an advanced intelligent AI chatbot from scratch in Python. Now, this is not going to be an LLM wrapper. It's not just going to be a Hugging Face model that we pull and use. We're going to implement our own neural network in PyTorch from scratch, which is going to classify the intents of users based on their messages and then respond in a predictable way or even execute functions if we want that. You can learn a lot about machine learning by implementing this project, and I think it's great to have it in your resume. It's actually one of the 5 project ideas that I presented recently in a video called the top 5 machine learning projects for your resume. If you like my videos and want to support this channel, make sure you hit the like button and subscribe. But now, let us get right into it. Alright, so we're going to build our own highly customizable, advanced, intelligent AI chatbot from scratch in Python today. Now, when I say from scratch, I mean we're going to use PyTorch. We're not just going to pull a model from Hugging Face, some LLM or something. We're going to define the architecture manually. We're going to do the training manually. We're going to do the inference. We're going to write our own data set. We're going to do all of the pre-processing. So this is not just going to be a plug and play type of video. We're going to actually implement everything from scratch here. Of course, not just in NumPy. We're going to use PyTorch for the machine learning part, for the backpropagation and optimization and so on. But besides that, we're going to do everything manually. Now, I want to get right into it, and I want to show you what we're going to build by showing you my example data set here. So this is my intents.json file. The basic idea of this chatbot is going to be, it's going to take a user message, it's going to classify the intent of the message, so what kind of category of message is this, and then it's going to deliver a static response and call a function if we wanted to. But the basic structure of this data set is the following. We have a dictionary object, then we have a key intents. This key points to a list, and this list contains dictionaries, and each dictionary has a tag, patterns, and responses. Now, what you need to understand here is that the responses are static. So these are the responses that the model is going to be able to produce, but the patterns are dynamic. So these are just examples which we're going to use to train the model, but these are not the only user messages that the model is going to recognize. For example, if I have the patterns down here, what is programming, what is coding, tell me about programming, tell me about coding, and what is software development, I can also ask something like, give me information about software engineering, and it's still going to be able to classify this as programming and give me this static response here. So programming, coding, or software development means writing computer code to automate tasks. So the user doesn't have to provide an input message or a request that is already part of this list here. It just has to be more similar to this list than to the other list. So if I have maybe programming and then I have another one, software engineering, then of course it's maybe going to be classified as the other one. But if it's the most similar to this type of group here, to this type of category here, it's going to be classified as programming. I'm going to get the static response, and if I want to, I can also call a function, which makes sense, for example, for the stocks intent, because what we do here is the user asks something like, what are my stocks? Which stocks do I own? Or show my stock portfolio. As a result, we get, here are your stocks. And this one is going to call a function that is going to fetch the stock data and display it to the user. So we don't have the same response every time, but we have a dynamic answer. So this is going to be function calling. That is what we're going to build in this video today. Before we get into the code, I would like to briefly show you here in my paint what this is going to look like in terms of the architecture. We're going to have some AI. This is our chatbot. And this AI needs to produce the classification. So the AI itself is not going to generate any text. Remember, our responses are static. So if I go into the JSON file, these responses here are static. They are not generated by the AI. It's just the AI predicts the tag, and then the response is chosen here from the list. So the AI itself will just give us a classification. But of course, the AI has to work with numbers. The neural network has to produce numbers. And what this neural network will do is it will give us the probability for each individual intent. So we have greeting, goodbye, programming, resource, and stocks. These are 6 different, or actually 5 different classes. So it would do something like this. It would say 0.01, 0.02. Then it would do something like 0.95, and then it would do 0.01, 0.01. This would now basically say that the probability that programming is the correct classification is 95%, and then we have 1, and 2% chance for the other classification. So this is going to be a so-called softmax output. We're going to take a look at that when we implement this. but this is what our AI is going to produce. And based on that now, I'm going to say, okay, what's the maximum argument? Okay, it's the index 2. What is the index 2? It's my programming intent. So I can go to the JSON file, go to tag programming, and pick the response and show it to the user. That is the output. But the tricky part is, what do we put into the AI? So what do we actually put into our neural network in order to do all of this classification stuff? So I can, of course, not just take a message like what is programming and feed it into the neural network. It doesn't work like that. So what the neural network will accept is just numbers. And I have to somehow take this message and turn it into meaningful numbers. And I'm going to go back to my paint once we're implementing this part. For now, I don't want to confuse you too much with the theory, but keep this in mind that this is a problem that we need to solve. And this is exactly what we're going to do now in the coding part. So first of all, we need to install some dependencies. We're going to use pip or pip3 install to install torch, to install numpy, and to install NLTK, the natural language toolkit. So just install all of this, and then we're going to open up a main.py file. And in this main.py file, we're going to do some imports first. From core Python, we're going to import OS, we're going to import JSON, we're going to import random. Now, why do we need those? OS just to check if something exists, JSON to work with a JSON file. Random is going to be used to pick a random response from the intents file if we have multiple responses in the list. Then we're going to import NLTK for the tokenization and lemmatization of our sentences. When we take a text like what is programming, we need to split it up into individual tokens or words like what is in programming. Then we're also going to import numpy as np. And then we're going to import torch. We're going to import torch.nn as an n. We're going to import torch.nn.functional as f. We're going to import torch.optimization as optimization, so as optim. And we're going to say import, or actually from torch utils.data. We're going to import the data loader and the tensor dataset. So these are the things that we're going to need. All of the torch stuff will be relevant to define our neural network, to train it, to do all the steps, to optimize, to create a data set out of our JSON file. So all of this is necessary for the machine learning part. NumPy is also just for working with arrays. NLTK is, as I said, important for the tokenization and lemmatization of words. By the way, one thing that you're going to have to do if this is the first time you do something like this in NLTK is you need to say nltk.download, and then you need to provide the string in here _tab. So like this. This is something that you have to run a single time, then it's going to be downloaded. If you don't run this and you don't have it on your system, NLTK is going to tell you that it's missing a package and you have to download it. But once you have done that, you don't need to run this every time. So one time is enough. And then we're going to start by defining our model architecture. So we're going to keep it quite flexible. We're going to say class chatbot model. It's going to extend from nn.module. And what we're going to do first is we're going to define the constructor. So the init method, which is going to take self, input size, and output size so that we can keep this flexible. And what we're going to say is, first of all, constructor here, chatbot model, parent class constructor has to be called like this. And then we're going to define the parts of the architecture, and then we're going to use them in the forward function. So I'm going to say here, self.fully connected layer 1. So FC1 is going to be NN linear, and the dimensions are going to be input size and 128 neurons. So the basic idea of this is we have some input size. Remember, we didn't discuss yet how to represent the text as numbers, but we're going to have some input size, some array of numbers that is going to be fed into this neural network. Then we're going to turn this into, or we're going to feed all of this into 128 neurons, which are going to be the first hidden layer. Then we're going to have a second fully connected layer here. By the way, for those of you who are familiar with TensorFlow, a linear layer or a fully connected layer is basically just a dense layer in TensorFlow or Keras. So here we're going to say linear. We're going to take the 128 neurons. We're going to feed them into 64 neurons here. So this is the second hidden layer. And then we're going to have a fully connected layer 3, which is going to take 64 inputs and it's going to turn them into output size. So depending on how many intents we have, in our case we had 5, but of course you can extend this, then you're going to have not 5 output neurons, but 10, 15, 20, whatever you want to have. But this is basically the number of intents. This is the number of output neurons for our network. Remember, in my little graph here, this was basically the length of this list here. So the length of this, in this case 5, but of course this can be different and we want to keep it dynamic, which is why we pass it here as a parameter. Now, in addition to that, we need an activation function to break linearity. So I'm going to say self.ReLU is going to be equal to NN ReLU. This is just rectified linear unit. For those of you who don't know what ReLU is, it's basically an activation function that looks like this. So we have a coordinate system and every input that is below 0 is going to output 0. And once we get to the positive numbers, we're just going to have the identity function. So for an input X, the output Y is also going to be X. So that's basically same input, same output. Quite simple. And the reason we use an activation function is to break linearity. If you don't understand that, I have a video where I explain this in mathematical detail. But if you don't want to watch this, just trust me that you need to break linearity. Otherwise, you just have a linear combination of the inputs, which is not very powerful when you want to have a sophisticated solution. So we're going to use that. And we also want to have dropout, a simple dropout layer, which is just going to be 50% here, so 0.5 probability of something not being included. This is just for regularization. You can play around with the architecture. You can add more layers. You can use no dropout layer. You can change the number here as well if you want to. But this is going to be the architecture that I'm going to use. And now we define the forward function, which is basically the forward propagation. When we get an input, how do we get to the output? For this, we pass self and X here, X being the input. And all we want to do here is we want to take X, feed it through the first layer, then apply ReLU, then apply dropout, feed it through the second layer, apply ReLU again, apply dropout again, and then feed it through the last layer, but not apply ReLU because we want to have softmax later on. So I'm going to say here, self.fullyConnected1 applied onto X, and then on top of that, we're going to call ReLU. So this is going to do the weights and biases calculation. So it's going to multiply with the weights, it's going to add the bias, and then it's going to apply ReLU to break linearity. Then we're going to say self.dropout. And then I'm going to just copy the first line. I'm going to paste it. Oh, this was not what I wanted to do. There you go. I'm going to do fully connected 2. So now we do that with the second layer. I want to apply another dropout then. And then I want to do the same with the third layer, but this time I don't want to apply the ReLU function because these are my logits for the softmax. Remember, we want to have output probabilities, so we are not going to apply ReLU. We're going to apply softmax, or it's going to implicitly apply softmax in the loss function, but that is our model. This is just the architecture that we're going to use now, but we still haven't covered how we're actually going to take the text and represent it as a list of numbers. So this is what we're going to do in our second class, which is going to be the chatbot assistant. So the model is just a model and the assistant is going to use that model. So we're going to say in the constructor, we're going to have the self keyword. We're going to have the intents path. This is just a path to the JSON file that we're going to use. And then we're going to have function mappings equal to none by default. And these are basically just going to be the mappings from intent to function. If we want to have specific functions that are being called when certain intents are recognized, we're going to pass them here as a dictionary, but we're going to care about this later on in the video. For now, let's just say self.model is none by default. Self.intents path is equal to intents path. Self.documents is going to be equal to an empty list. Self.vocabulary is going to be equal to an empty list. Self.intents is going to be equal to an empty list. Self.intents responses is going to be equal to an empty list. Self.function mappings is going to be equal to function mappings. And then self.x is going to be equal to none. Capital X and lowercase y is also going to be equal to none. We call this capital X because X is usually a matrix and Y is a vector. So Y is just the output vector and X is a matrix. So this is why we use capital X but lowercase y. And why do we have now documents, vocabulary, and intents here as lists and intents responses? Now, intents and intents responses is quite clear. This is just a list that we can choose from for the output. This is also what we need in order to assign probabilities. But documents and vocabulary are interesting because we're going to use them actually to turn our example sentences into numbers. And for this now, we're going to define our first static method here, which is going to be tokenize and lemmatize, which is going to take text as input. It's going to be a static method, so it's not going to rely on any object attributes. So we're going to add this decorator here, static method, tokenize and lemmatize. And we're going to say now that the lemmatizer is going to be equal to nltk dot word net lemmatizer. And we're going to say that the words are going to be equal to nltk word tokenize. So we're going to take a sentence or a text and we're going to extract the individual tokens or words, and then we're going to lemmatize them. So we're going to reduce them down to the word stem. So instead of having 10, 20 different variations of the same word, we're going to just reduce them down to the basic word that is the stem of the word. So we're going to say here, words is equal to lemmatizer dot lemmatize word dot lower for word in words. You can also call this token if you want to. So basically what we're doing is we're taking a sentence and we're splitting the sentence into individual words, and then we're taking these individual words and reducing them down to a stem word. And we're also ignoring the case. So actually maybe we can use that. Maybe I can go ahead and create down here an instance. Let's say chatbot is equal to chatbot assistant. Let's provide intents.json as the path, and let's just say chatbot.tokenize and lemmatize. Hello world, how are you? I am programming in Python today. And then we can actually take that, and of course we want to return the words. And when I run this now, this should give me the tokenized and lemmatized words. So, oh, actually, of course, I need to print the results. But there you go. You can see, hello world, how are you? I am programming in Python today. Now, these were all already stem words. So let's try something else. Let's do run, running, runs, ran. And let's see what we get when I tokenize and lemmatize this text. In this case, we're going to get run, running, run, and ran. So running is different than run. Runs is not different from runs. So run and runs are not considered a different word stem. But of course, running and ran can be different because they're a different time or a different tense. And because of that, it makes sense to differentiate. But you can see that some words that are not the exact same token will end up being the same word stem or the same stem word. So this reduces complexity, makes stuff simpler. But of course, we still have the problem that we're working with tokens or words and not with numbers. So what we need to do in the next step is we need to turn these tokens into a numerical representation. And for that, we're going to apply the bag of words strategy. So I'm going to say here static method. The second method here is going to be called bag of words. And this is going to require a vocabulary. So let me pull up my paint again. Now it's time to explain the actual encoding process. So what we're basically doing is we have a vocabulary of all possible words. So I'm going to do this here in turquoise. Let's say this is my vocabulary. And in this vocabulary, I have all the words that I know. For example, the first position in that vocabulary could be the word what. And the second one could be I. And the third one could be, I don't know, programming. And the fourth one could be run. And the fifth one could be hi, or something like this. And I have all the different words that I know. This is my vocabulary. Now, all of these words can be also considered to just be an index. So what is index 0, I is index 1, programming is index 2. And what I can do now is I can encode a sentence in terms of these vocabulary positions. So I can say, for example, that a sentence is a representation, it's a list where each position represents a word. So that would be what, that would be I, that would be programming. And all I do is I just set them to, programming, I set them to zeros and ones. So I say if my sentence is what is programming, I will set a 1 for what, I will set a 1 for programming, I will set a 0 for I, 0 for run, 0 for hi, and so on. Then at some point I'm going to have the position for is, and that is going to be a 1, and everything else will be a 0. So I'm going to have a list that has a bunch of positions. A lot of them are going to be set to 0, some of them are going to be set to 1, and this is the numerical representation of a sentence. Now, this is of course not necessarily the best approach, but it's simple and works good enough for our purposes. Of course, this does not consider the order of the words. So what is programming, or programming is what, would be the exact same sentence in this case. And also, if I include a word multiple times, it's not going to be considered differently. So we're not going to increase the number here. We're just going to say yes or no. But this is enough to make our chatbot intelligent and classify the intents correctly. So this is the bag of words idea. So what bag of words is going to take as parameters here is going to be words and a vocabulary. And then it's just going to return the following. 1 if the word is in words. 4 word in vocabulary. And of course, we need to say else 0. So we go through all the words in the vocabulary if the word is part of the words that we're trying to encode. So if my words object here is what is programming, then I check, okay, for every single word in the vocabulary, is it part of this list? And if it is, I'm going to set 1 at that position. Otherwise, I'm going to set 0 at that position. So this is basically going through all the words I know and checking if these words are part of this words collection here that I'm trying to encode. That's the basic idea. So to summarize the process, we take a sentence, we split it into individual tokens or words, we then lemmatized these tokens or words, so we reduce them down to the word stem, and then we encode them using bag of words into zeros and ones, representing a yes or no for every single word in the vocabulary. Now, what we need to do next is we need to actually get the data from intents.json and prepare it. For this, we're going to write, first of all, the method parse intents. All we're going to do here is we're going to pass the self keyword, and we're going to load the data from our intents.json file. So I'm going to say, again, lemmatizer is equal to nltk wordnet lemmatizer. I'm going to say if os path exists, and then self.intentsPath. Then we're going to load this file. So I'm going to say with open self.intentsPath in reading mode sf. I'm just going to say intents data is equal to JSON load f. So now we have a JSON object with the entirety of the JSON file in it. So this is a dictionary that contains intents and a list that contains dictionaries. And now we need to parse the intents for our purposes. So what we're going to do here is we're going to say intents is an empty list. Intents responses is an empty list. Vocabulary is an empty list, and documents is an empty list. And then we're going to iterate over the intents and fill up these lists. So we're going to say for intent in intents data intents. So that is now going to be the dictionary that contains tag, patterns, and responses. Every single intent is going to be a dictionary that contains these 3 fields. And now we're going to do if the intent tag is not already in intents. So if we haven't seen it before, we're going to say intents dot append. We're going to append the intent tag. So we're not going to allow for duplicates. We're not going to override previous entries. If a tag occurs multiple times, we're just going to append it once. And then we're going to say intents responses intent tag. And here now we're going to set this equal to intent responses. So basically we're going through the intent, we're saving the tag greeting, for example, into the intents list, and then to intents responses, we just set this collection of responses as a value to the key, which is the tag. So this is a dictionary. Actually, I need to turn this into a dictionary. So the tag greeting is going to be mapped to the responses, hello, good to see you again, and so on. Now, after that, we're going to say for every pattern that we have. So this is, again, what we want to now encode using back of words, because we don't want to encode the responses. The responses are just going to be static answers. But this is what we trained the neural network on. So we need to actually take all of that and turn it into a numerical representation. So for pattern in intent patterns, we're going to say the pattern words are going to be equal to self.tokenize and lemmatize pattern. This is now the function that we're using up here, the method. We pass the text, we lemmatize, we tokenize, or tokenize, we lemmatize, then we return the words. That is what we get here, pattern words. And then we say vocabulary extend pattern words. So we add all the words that occur in this sentence to our vocabulary. And also we say documents append pattern words intent tag as a tuple here. So a document is basically the entire thing. I need to model this as a tuple. Come on. So like this. So every document is the combination of the words and the intent. This is like our X and Y data in a single tuple. Now, since some of the words are going to occur multiple times after we have processed all the patterns, we need to say vocabulary is equal to sorted set of vocabulary. To eliminate duplicates, we use set, and to then turn it into a sorted list, we use sorted. So that is now a sorted list with unique words. This is every word only occurring once. Now, I see that in my prepared code now, I have just assigned all these things to my object attributes, but I think it's actually more reasonable to use self-intents directly, so we don't really need to do anything because all of these occur already up here, just that I need to turn this into a dictionary. So let's delete all of this here. Let's do actually not in self.intents. I have a couple of typos here. So to explain what we're doing here one more time, we're looking for the intents file, we're loading it as a dictionary, and then we iterate over all the intents that we have over all the dictionaries, and then we say if this tag, the tag of this dictionary, so if this field here is new, it doesn't already exist, not in self.intents, then append it to self.intents. So self.intents. Self.intents, and then also we need self.intents responses here. So basically we're adding the tag to the list of intents, to the list of tags. Basically we're adding the responses, the possible responses to choose from, to this dictionary here, and then we say for pattern we want to get the pattern words, and we want to say self.vocabulary extend, self.documents append, and self.vocabulary is equal to sorted set self.vocabulary. So instead of using them before the loop and then setting them, we're just going to use them directly. We're going to say that we already initialized them here, so we're going to use them right away. All right. So now we have a filled vocabulary with unique words. We have documents where we have X and Y data as tuples. We have the intents list, and we have responses to choose from for each intent. What we need to do next is we need to define a method, prepare data to actually turn this into data that we can use in our neural network. So this is going to be with a self keyword again. And now what we do is we actually say the bags that we're going to use, and the indices that are going to be our ground truth are going to start as empty collections. And now all we need to do is we need to say for document in self.documents, the words that we want to encode are going to be the first element of the document. Remember, X and Y. So the words are going to be this here, pattern words, index 0. So words is equal to document 0, and the bag is going to be self.bag of words. So we're just going to use our static method here to take the words and turn them into ones and zeros. So we're going to say words and self.vocabulary. By the way, this is maybe another thing that we can improve. Maybe let's not model this as a static method. Let's say self and words, and let's say self.vocabulary. Makes more sense. So then we're going to do self bag of words. Words, this is going to turn them into zeros and ones. And then the index, the correct index, is going to be equal to self-intents.index. And where is the tag? Of course, it's the second position. So index 1, it's going to be document 1. Because again, I'm repeating things multiple times because I want you guys to be able to follow that. Here we filled up the documents with the words and the corresponding tag. So this would be what is programming. This would be programming. And then what I do here, I turn this into zeros and ones based on the vocabulary. And here I would get the numbers. So I'm getting programming and I'm asking what is the position of programming in my intents list? What's the index? In this case, it would be 2. And because of that, now I would have 2 here, and I would have a bunch of zeros and ones as a bag here. So then we're just going to say bags.append, bag and indices dot append intent index. And finally, once we're done with all of that, we're going to say self.x is equal to np array of bags, and self.y is equal to np array of indices. So our X data will just contain a bunch of bags of words, and the Y data is just going to be a vector of the correct predictions. And basically that's it for the data preparation. The only thing that we need to do now is we need to train our model with that data. So we're going to define the next method, which is train model. And here now we're going to pass a bunch of parameters. First of all, the batch size that we want to use, also the learning rate that we want to use, and also the number of epochs. So the learning rate is basically how quickly our model is going to move into the direction of steepest descent. Then the batch size is how many instances we're going to process in parallel at once. And then epochs is going to be how many times we see the same data. So I'm going to say here the X tensor is equal to torch.tensor of self.x. The data type I want to use here is equal to torch float 32. Since these are floating point values, our Y tensor is equal to torch tensor self.y. But this data type here is not a floating point because we're using just integers. So we're going to say torch.long. And then we're going to create a data set based on our X and Y tensors. So I'm going to say here data set is equal to tensor data set. This is what we imported in the beginning based on the X tensor and the Y tensor. And then we're going to create a loader, a data loader based on the data set with a batch size. Come on, with a batch size equal to batch size and with shuffle equal to true. So now we have a data loader for our data set, which is basically just our X and Y tensors. Remember, if you lose track of that, X is basically just the bag of word representation of all the different sentences, and Y is the correct classification. So that is just what we're loading here. And then we say self.model is equal to chatbot model. And we're going to say that the input size, this is now interesting and important. what do we actually feed into our network? The input size is going to be the size of our, or the shape of our x values. So it's going to be whatever our x values are. And in this case, it's going to be self x shape 1. So what are the dimensions of one bag of words? And this, of course, depends on the vocabulary. So this is going to be determined by how many different words we see. And we can just get this dynamically by saying self x shape 1. Shape 1 means the dimension or the size of an individual bag of words. Shape 0 would be the amount of bag of words or the amount of bags that we have. But an individual bag has the shape that we get by using index 1 here. And then the output shape is going to be just length of self in tens. Now, it's important to understand here that we're actually using indices, but behind the scenes, the cross entropy loss that we're going to use here in a second is going to automatically do softmax. It's going to automatically turn this into the encoded representation with the probabilities that I talked about, remember, this year. This is going to happen automatically by using the loss function. So we need to say that the output dimensions are actually going to be length of self in tens and not just an individual number the way we pass it here as a tensor. So our tensor is just per instance one number, like 1, 2, 3 or so, or something like this, or 0. But the output of the neural network is actually going to be a probability for every single class, for every single intent. So it's important to pass length self-intents here. And now we're going to define the loss function. The criterion for optimization is going to be nn.cross-entropy-loss. And the optimizer that we're going to use here is going to be equal to optim atom, the atom optimizer. We're going to optimize the parameters of the model. So self-model parameters is what we're trying to optimize. The learning rate here is going to be equal to the learning rate we pass to train model. And now everything is set up properly. So we're going to say for epoch in range epochs, I'm going to say running loss is equal to 0.0. And then we're going to process in batches. Now our data loader is going to give us batches of data, not just individual instances. So for batch X, batch Y, in loader, we're going to say optimizer.0grad. So we're going to set all gradients to 0. Then we're going to calculate the outputs of the current neural network. So for those of you who are not familiar with neural networks, how it works is you basically start with random weights and biases. So you have parameters that are completely random, or I mean, there are some initialization methods that make more sense. They're not completely random. There's most of the time some distribution, but in this distribution, they're random. So it's just meaningless weights. But what you do is over time, you improve these weights and biases, these parameters, to make more reasonable predictions. So in the beginning, it's going to be random, but what we do is we see with these random parameters, what does the model say? So we say self-model applied onto the input X. So these are the bags of words. We apply the model and we get some outputs. And what we do in the next step is we want to know how wrong are these random outputs. So I'm going to say loss is equal to criterion, and we compare what the model outputs to the actual truth. So this is what our model produces with the randomly initialized parameters, and this is what we wanted to produce. This is the ground truth, the optimal true result. And what we do then is we back propagate this. So we say loss.backward to take the loss and propagate it through the network so that we get the gradient and the error, so to say, the direction of improvement for every single parameter in the network to see where it was wrong about this. This is basically the chain rule of calculus. But what we do with this information then is we take the optimizer and we take a step into the correct direction. Now, how large the step is depends on the learning rate. If the learning rate is very small, we're going to just take a tiny step into that direction. If we choose a large learning rate, we're going to take a huge step into this direction. So it depends on the learning rate, and yeah, the learning rate that we're going to choose is going to be something like 0.001, which is going to be fine. And then what we want to do is we want to add all of the loss to the running loss to keep track of that. So running loss is going to be plus equal to loss. And then we're going to just print the information here every time for every epoch. So we're going to say print. Let's use a formatted string. Let's say epoch, and then we're going to say epoch plus 1. Loss is going to be running loss divided by length of the loader, and we're going to round to 4 decimal places here. That is just going to see, or that is just in order to see how our loss improves over time. And that is basically the training. Now, what we also want to have is 2 methods for loading and saving, or for saving and loading. So we're going to have a save model method here, which is going to take a model path and a dimensions path. And what we're going to do here is we're going to say torch save self model state dict. So the state dictionary of the model. And we're going to save this to model path. And then we want to say with open dimensions path in writing mode SF. We want to say JSON dump. And we want to dump the following dictionary. The input size is going to be equal to self.xshape. This is again what I talked about, the dimensions of a single bag of words. I'm going to, by the way, repeat all of this one more time before we actually get to the demonstration, because I think it's important to mention the same things over and over again so that they stick. So here, length of self-intents. That is the dictionary that we're going to write into this file. And we need to, of course, also pass the file pointer f here. And then we want to have a second method, load model, same parameters, model path, dimensions path. And here we're just going to say with open dimensions path in reading mode SF. Dimensions is going to be equal to JSON load the file. And then we want to say that our model is equal to a chatbot model instance. The dimensions of that are going to be, or actually I should say the input size, or it's a positional parameter. So let's say dimensions, input size, and dimensions output size, like this. That's why we export it in the first place, because in order to use the weights, we need to have a model that we can load the weights into. So we need a model with the same dimensions, with the same input size and output size. And because of that, we also want to export and import this information. So that's going to be this, and that's going to be this. And now we want to say self.model load state dictionary torch load model path weights only equals true. That's about it. Now, last but not least, the final method that is important now for our assistant is to actually process messages. So how do we now answer a request? We have this process message method here, which is going to take an input message, and it's going to use the trained model to make the right decision. So it's going to say words is equal to self.word, or what was it, tokenize and lemmatize input message. So we do the same pre-processing here, or the same encoding. We need to take the input message, split it into tokens, reduce them to the word stem, and then we're going to say that the back representation of this input message is bag of words input message. And then we need to say back underscore tensor is torch.tensor. We're going to pass the back here with a data type of torch float 32. So we're basically doing the same thing that we did with our X data, but this time we only have a single instance. So we do the same thing that we did here. And we're taking that. We're putting the model into evaluation mode. So self model eval. We're saying torch no gradient calculation because we're no longer training. So with torch no grad, the predictions are going to be equal to self.model back tensor. And the result of that is going to be the softmax output of our model. So we need to say predicted class index is going to be equal to torch argmax. This is going to take the index with the highest activation. So you can also, if you don't want to take the index with the highest activation, you might also want to do a random decision based on the probabilities. So maybe weighted randomness, but I'm just going to get, I'm just going to go with the most likely response, or with the most likely classification. So I'm going to say here predictions and dimension equals 1. Dot item, this is going to give us the predicted class index and the predicted intent. So the actual word that we're looking for is equal to self intents and then that index. So this right here then is going to be our string, like greeting, programming, stocks, or whatever. And this is what we're going to use now to get a response. So we're going to say, first of all, if self.function mappings, if I have some functions that I assign to this specific, so if I defined up here in the constructor that I want to have a certain mapping between, for example, stocks and a specific function, I'm going to run that. And in order to do that, I need to say if self.function mappings, if I even have mappings, then if this predicted intent is part of my function mappings, if that's the case, then we're going to go to the function mappings, get the function that is mapped to this intent, and call it. So we're going to use these parentheses here to basically call that function. And if not, we're just not going to do anything. So then we want to say if the intent responses for that predicted intent are not empty, we're going to return a random choice. So I'm going to say random choice self intent response, or intent responses for that predicted intent, which makes sense if you have multiple instances. That would mean, for example, if I have like here, hello, good to see you again, hi there, how can I help? It's going to take that and make a random choice. For example, this one. And otherwise, we're just going to return nothing. So maybe I have some tags, some intents here where I don't have responses because all I care about is the function call. In this case, I'm just going to return none. And that is, I'm sure I made some mistakes. We're going to fix them when they come up, but that is basically our assistant. So let me go through all of this one more time. We have our model, which is just the architecture. We have an input size, which is the dimension of our bag of words. Then we have 128 neurons connected to 64 neurons connected to the output size, or to output size many neurons, which are just the probabilities, or which are going to represent the probabilities for every single intent. So this is going to be equal to the number of intents. We have an activation function. We have a dropout function. We just feed the information through the network. And what we do is we take the text, be it an example text, be it the patterns here, or be it a user message. We take that, we split the text into individual words or tokens. We reduce the token down to the word stem to make things simpler. We then encode it as zeros and ones. The vocabulary is all the words we know. Every word is mapped to a position. A 0 in that position says this sentence does not include this word. A 1 says this sentence does include this word. And what we do is we go through all of the patterns, we encode them, and we encode them down here in prepare data. But what we do here is we take all the JSON content, we save all the intents, all the responses, we build the vocabulary, we save the documents. Every document is the words and the correct classification tag in a tuple. In the prepare data function, we take all these words, so all these pattern words that we save here in the first index in the tuple, we take them, we encode them as bags of words, so as zeros and ones. The intent tag is then the actual index, the actual intent. We take that, we turn it into a number as well by taking the position of that specific tag, and then we turn that into NumPy arrays to train the model, return all of this into tensors. We define a data set, a loader. We create our model with the respective input and output shapes. We use cross entropy loss. We use Atom as the optimizer, and we just do the basic stuff that we do with neural networks, where we have a randomly initialized model, so random weights and biases, and then we just calculate the difference between the output that the model produces and the output that we want the model to produce, and we backpropagate this error, this improvement through the network. We take a step with our optimizer, and over time, over a large amount of epochs, we're going to improve our model so that it actually behaves intelligently. We can save it, we can load it, and to process a message, we take the input message of a user, do the same thing, tokenize, lemmatize, bag of words encoding. We feed that through the network. We get as a result the softmax probability, so this here. And what we do with argmax is we just take the index of that correct classification, and then the intent is actually the word programming, and we see if we have a function mapping here, and then we also see if we have responses, and we return the response and we call the function. That is the magic behind it. Now let's go and actually use this. So what I'm going to do here is I'm going to define a getStocks method. This method is just going to, I don't know, let's do some randomness here. I don't want to actually use Yahoo Finance here. So let's say we have some stocks, Meta, Apple, Nvidia, Goldman Sachs, Microsoft, and so on. And then let's just return random sample, or should I go with, no, random sample stocks, and then let's go with 3. So I'm not sure if the last one is also required, but let's just do it like this. And then let's say if underscore underscore name underscore underscore is equal to underscore underscore main underscore underscore, then we want to actually use all of this now. So I'm going to say assistant is equal to chatbot assistant. The intents path is obviously intents.json. And the function mappings are going to be equal to stocks shall be mapped to getStocks. Now it's important we don't call getStocks, we pass it as an entity. So we take that function and we pass it as something that can be called. And then what we do is we say assistant.parseIntents. We say assistant.prepareData. We say assistant.trainModel. Now here we provide a batch size of 8, a learning rate of 0.001, and we want 100 epochs. And in the end, we want to say assistant safe model chatbot underscore model.pth and dimensions.json. Now, I'm sure we made some mistakes. Let's see, we have here invalid syntax, line 70. Yeah, because I should say not in intents, not in self-intents, obviously. I think I fixed that before. Maybe I undid my fix again. Let's run this. Okay, another mistake is, where is this? This is 115. Oh, so I see the big mistake here. We need to, of course, return the output in the forward method. We do all the correct steps here, but we need to return the result as well. Otherwise, we have none. So let's run this again. Okay, so the training worked well, but we still have a problem with safe model. Let me see what that is. Safe model. Oh, I indented this incorrectly. All of these need to be shifted one to the left. So let's run this again. There you go. So we trained the model and we saved the model, but we didn't interact with the model. So in order to interact with the model, we can say while true. Then we can say message is equal to input. Enter your message, colon, and then if message is not equal to, let's say, /quit, or actually, let's say if the message is equal to /quit, then we want to break. Otherwise, we're going to say print assistant process message. And I found one more very important problem here. In process message, we're getting the words and then we're doing back of words, but we shouldn't do that on the input message. We should do that on the words. So we get the words and then we do back of words onto the tokenized and lemmatized words. So let's run this now and let's see what we get. Hi, hi, hi. You can see I get a random response every time. Now let's do what is programming. Programming, coding, or software development means writing computer code to automate tasks. Then we can also say something that is not in the training set, like what or give me information about software engineering. Programming, coding, or software development means writing computer code. See you. Talk to you later. Then I can say show my stocks. Here are your stocks. Now, this is something that we probably need to do better because, of course, our getStocks method just returns a sample. We don't want to return a sample. We want to print a sample because we're calling the function. We're not getting the value of the function. So I can actually run this again. Now I can say stocks, and here I get Apple, Goldman Sachs, and Microsoft. I can do stocks again. I can do finance. Okay, no, finance is not recognized. So it's not about the similarity of the words. It has to contain actually similar words. But I could ask something like, I am wondering what stocks I own. Here are your stocks. So that works, but it's of course not perfect in terms of similarity. So if I ask what are my assets, it's not going to probably, or maybe because of the what are my, it's going to recognize it. But I don't think that if I just type assets, it's going to give me my stocks. No. Okay. So that works. And what we want to do now is we want to actually load the model without having to train it every time. So I'm going to actually comment this out. I'm going to just use this here again to define the chatbot assistant. And then I'm just going to load the model from the file. So I'm going to say assistant parse intents. This is important because I need, of course, to have the responses from the JSON file. But then I'm going to say assistant load model, chatbot model, PyTorch, and dimensions dot JSON. And now let's see if it still works the same way. Now I don't have to train anything. Hey, what are my stocks? Perfect. Then what are good sources to learn coding? Check out Neural 9 YouTube channel and the Python Bible series. Perfect. What's coding? Okay, it doesn't recognize that. What is coding? Now it tells me that. So, of course, you can improve this. You can train for more epochs. You can have more examples. You can also add some additional mechanism for similarity, maybe, if you want to have not just the exact same words in a bag of words, but you also want to have some similarity, which would make things more complicated, of course. But this is how you can build an advanced and intelligent AI chatbot from scratch by defining your own architecture, by doing all of the pre-processing and training yourself. And if you take that now and extend it with your programming knowledge by implementing maybe named entity recognition, by adding additional stuff like similarity of certain terms into that, you can make this a very impressive resume project. If you just copy paste my code now, it's not going to be a very good project because you're just copying and pasting code. But if you extend this now, make it more interesting. So let me know in the comment section down below if you would like me to make an additional tutorial, which is more comprehensive, where I also include stuff like named entity recognition, where you can also program your model to extract certain keywords and certain values, like, for example, answering the request, give me the price of 5 bananas, to extract the 5 and the bananas and then do a lookup and then return the price dynamically. This is more advanced. Let me know in the comment section down below if you would like to see something like this. But that's it for this video today. This is how you can build an intelligent AI chatbot in PyTorch from scratch. So this was a quite comprehensive tutorial. I hope you learned something. I hope you can take this now and apply it to something, or take this and extend it to have an interesting project for your resume. Let me know in the comment section down below if you would like to see a more advanced version of this tutorial, maybe including named entity recognition or something else. If this video performs well, I'm going to do something like this. Otherwise, I'm going to focus on different projects. As always, if you want to support this channel, make sure you hit the like button and subscribe. And besides that, see you in the next video.